Hi, my name is Masi Bauchi. I'm a professor at UCLA, and I'd like to tell you about the work that we have been doing on using machine learning to decarbonize concrete at scale. And the reason for this is, of course, that concrete has a very large carbon footprint, and sometimes we don't realize how large the carbon footprint of concrete is. But one way to realize this is that if you take all the emission due to concrete, it's 4 times larger than all the emissions due to the aviation sector. So there's really an urgent need, especially as other industries are decarbonizing, to decrease the carbon emissions due to concrete. And so there's various ways that you can do that using new materials, new processes, etc. But what our approach has been to see what can we do now? Like what can we do with the materials that we have today? What can we do with the plants that we have today and with the way, without changing the way we are making concrete today? Like how can we decrease the carbon footprint of concrete? And one way to do that is to use recent advances in AI and machine learning. And the idea behind this is that we already know how to optimize concrete, how to make it greener. The way to do that is to adjust the mixture proportion of concrete and find new formulation that can still meet the same strength, but with featuring a lower carbon footprint. And the problem with that is that it's a pretty low and slow and laborious process. Like the idea is that to discover a new concrete formulation, typically you start with a mix that you have been using, and then you start changing something about this mix, maybe increasing the fraction of fly ash, reducing the amount of cement, maybe adjusting the gradation, trying to use some chemical admixtures, things like that. And then you need to do a trial batch to check that after this change, the strength is still there, that the slump is still the one that you want, etc. So you need to make a change in your concrete formulation and then trial batch the concrete, wait for 28 days. And then after that, either the strength is still there or it's not. And it's really a trial and error process where you need to try several times where every cycle is going to take 28 days to get the result, the lab result. And so this is really a slow process that you have to do mixed design by mixed design. So this is really here an opportunity for machine learning to change the way we are optimizing concrete and do this much faster than the typical way to do that. And so for this, what we've been doing is to develop a series of machine learning model that can predict the performance of concrete based on its constituents and based on the mixture proportions. And so the idea is that based on the physical and chemical characteristics of the materials and based on the amount of each materials in the concrete, we're able to predict the strength of concrete, but also other properties like the slump, shrinkage, etc. So this is really those machine learning models that allows us to bypass the need for systematic trial batch, because now with those models, we're able to directly predict for a new concrete formulation that maybe has never been tested in the lab to directly predict how it's going to perform, what its strength development is going to be, etc. And so here are some results. So here what I'm showing is some plots where I'm showing on the y-axis the predicted strength, the strength that is predicted by the machine learning model. And on the x-axis, this is the true measured strength. And the idea of this plot here is that if the model was perfect, everything would fall into this y equal x line, the line of equality. And so here, as you can see, I'm showing results in blue. Those are the concrete samples that were used to train the model. So in this case, it's not surprising that indeed the strength that is predicted for those samples is close to the true measured strength. But what is more interesting is that for the samples in orange here, those are samples that were never used to train the model, samples in the test set that have never been seen by the model. And the model is able to correctly predict with an accuracy typically of about plus minus 500 psi. And so we can do that for other performance properties as well. Like for example, we can predict the shrinkage of concrete. So there's some example here where we also have a good accuracy in predicting the shrinkage of various concrete samples. We can also do that to predict the slump with, again, an accuracy that is about plus minus 0.7 inches. And we can do that for other properties like predicting the air content, predicting the set time, the permeability, so other properties that are typically important to specify concrete. So now once we have those models, that makes it possible to optimize concrete, to reduce the carbon footprint of concrete without compromising on strength, without compromising on performance, slump, etc. And so the idea of that is that now, since you have the ability using machine learning to directly predict the performance of any concrete formulation, then using a high throughput approach, we can directly identify what is going to be the very specific formulation that's going to be either the most economical or the one with the lowest carbon footprint that's still going to meet all the performance target and all the requirement that producers have. And so here, what I would like to show you is a first example of a test that we did where the goal of this exercise here was to find a new concrete formulation with a strength of 5,000 PSI and a given target slump. And the way we did that is that we ask an expert quality control person to do this. And on the other hand, we did this design exercise with the AI that we designed. And so here the goal is kind of to compare what a human can do when optimizing concrete versus what the AI can do. And so here the goal again was to find a concrete mix that has the lowest possible carbon emission that meets a minimum strength of 5,000 PSI. And so here, as you can see, in green here, that's the mix that was created by the AI. And so it largely exceeded the target. So the mix that was identified by the machine learning model was indeed meeting the strength requirement. And one thing that was interesting is that the mix found by the human here in blue was actually slightly short on the strength, which shows that sometimes human can be greedy and try to optimize a little bit too hard, and eventually the concrete did not meet the required strength. And here in all of those plots here, I'm comparing the results with an NRMCA national average, which is the result in red here. So then another thing, strength is one thing, but we also need to make sure that all other engineering properties are properly met. And so here we had a requirement on the slump. And so all the free mix designs, so the reference from the NRSCA, the mix created by the human in blue, and the mix created by AI all met the slump requirement. One thing that's important is that AI was able to find the mix with the lowest embodied CO2. So here I'm comparing the embodied CO2 of the NRMCA reference in red. The one found by the human was actually slightly larger, more carbon emission than the one of the NRMCA reference. But more importantly, the mix generated by the AI, like what was featuring a 35% reduction in the global warming potential as compared to the one found by the human. So this really illustrates the potential of using AI to find some patterns in data that maybe humans can't see, and to really find some opportunities in reducing the carbon emission of concrete that would be very difficult to achieve, or that would take a very long time for a human to be able to achieve. And another interesting example here is that for those free mix, when we actually look at the cost of those free mix, the mix found by the AI was actually more economical than the mix created by the human. And this is because obviously one way to reduce the embodied CO2 of concrete is to reduce cement. And cement is the most expensive materials in concrete, but it's also the most carbon intensive. So usually when we are able to reduce cement, we can win both on the CO2 front, but also on the cost front. So here, those like greener concrete formulation that were found by the AI were actually more economical. So they didn't come with any kind of price premium as compared to the one found by the human. So now the challenge is that it's one thing to do it in the lab for one or two mixes, but how do we do it at scale? Because if you take a typical concrete producer in the US, they typically have like several hundreds of mix design per plant. And so each mix design has different requirements, different constraints, different materials, etc. So it's really a challenge to do it like really in a high throughput fashion at scale. And so this can only be done like with a more like a software solution that can do some kind of high throughput optimization of all the mix design of that are in the catalog of a given producer. And so this is why we developed this this website Concrete AI that uses AI to reduce the carbon footprint of the concrete of a given producer at scale in a high throughput fashion. So the idea is that it goes through the entire catalog of all the mix design of a given producers at all of their plants. And for each mix design is going to suggest a new optimized formulation. And so now in the remaining minutes, I would like to show you what this software looks like. So the idea of this software is that it connects to the quality control software that producers are using to directly get all the information about the materials that they have access to and all their historical test results. And based on that, is able to make some prediction and some optimization. So I'd like to give you a quick walkthrough here. So the first thing that we collect is some information about the plants that the producer has. And so for each plant, we collect various information, including the A3 contribution to the global warming potential, which allows us to accurately compute the global warming potential of each mix designs. And for each plant, we look at what are the available materials. And for each material, we collect some information about both the A1 and the A2 contribution of the global warming potential coming from both the manufacturing of the material itself and also its transport between its original plant and the concrete plants. And so based on that, by combining the A1, A2, and A3, we're able to accurately determine the total global warming potential of each mix design. So now, in addition to that, for each materials, we are collecting some information about its chemical and physical properties that you would find on the certification of each material. And here, for example, this is an example here for a granite coarse aggregates where we collect some information on its specific gravity, its absorption, fineness modulus, as well as the full detail of its gradation. So now that we have access to those materials, we collect some information about all the mix designs that are activated at each plant. And so like here, what we do is to collect for each of the plants of the producer, we collect some information about not only the mix design that they have, but for each mix design, we collect some information about the constraints and the target performance. So for example, here, this is an example of a mix that has a target of 6,000 PSI with a given over design. It has a given requirement on slump, a given air content, and also a requirement on pumpability. And so for this mix designs, we have the detail of all the constituents that are used, as well as the quantity of each constituents. And so now with this, what we can do is to directly predict the performance of this mix design. This is where the machine learning models comes to play. Since we have some historical data from the producer that we have used to train some machine learning models, we are able to predict the performance of any mix designs with any combination of materials and any fractions. So here, this is an example of the strength development that is predicted for this mix designs. And the prediction of the strength at different days, prediction of the slump, prediction of the shrinkage, setting time, etc. So this is really where the core of what we are able to do is those machine learning models that for any mix designs are able to predict the performance, the various characteristics of this concrete. But when that becomes, of course, extremely powerful, is that now we are able to take all of those targets, so the target strength, the target slump, etc. And we are able to use AI to find how to reduce the carbon emission of this mixed design. So like the way we do that is we look at all the possible ways to combine those materials together. So simply using the materials at the plant without adding any new materials, we are able to find the most efficient way to use all of those materials and to find the very mixed design that's going to meet all the performance requirements and all other potential constraints like water to cementitious ratio, water total cementitious, cement replacement, etc. And to do this in the most either cost-effective fashion or by minimizing the global warming potential. So we have different objective when we do an optimization. We can either minimize the cost or minimize the global warming potential. So let me show you in this case an example of global warming potential minimization, where the idea again is that in the background here, we look at all possible ways to combine those materials. And for each of those mixed designs, we compute accurately its total global warming potential using both the A1, A2, and A3 contribution to the global warming potentials. And then we look at all the mixed designs that satisfy the constraints. And among those, we look at the one that features the lowest possible global warming potential. So this is an example here of in this column that this was the original mixed design. In blue, this is the new mixed design that was created by the AI, where many things have been changed, like the amount of water is changed. It's changing here. It's transforming a binary mix that only contained fly ash and cement. It's transforming that into a ternary mix with slag, fly ash, and cement. It's adjusting the fraction of the aggregates. It's also creating a blend here between some natural sand and some manufactured sand. It's adjusting the fraction, the dosage of the plasticizer, and it's also adding a strength enhancer chemical admixture here. So it's really changing fundamentally the mixed design to create a brand new mixed design. And when we look at the predicted properties for this mixed design, indeed, it's predicted to have a strength that largely exceeds the target. It's predicted to have a slump that is close to the target. And so basically, this mix is going to meet all the requirements for this mixed designs. And so when we look at the actual global warming potential of this mix, so like without using any new material here, we're able to get like a more than 50% reduction of the global warming potential. So this really shows how simply by using those kind of data-driven approach without any new kind of manufacturing method or any new type of cement, anything like that, we can already like greatly reduce the carbon footprint of concrete simply by finding inefficiencies in the way we use materials and finding the most optimal way to combine those materials together. And another thing that is interesting is that here, once again, when we do that, not only we greatly reduce the global warming potential, but we also observe like a decrease in the price of the raw materials. So in this case, this greener concrete here does not come with any kind of price premium. So using this approach, we have already optimized more than 2 million cubic yards of concrete with a couple of producers that we are working with. On average, we have observed like a 5% reduction in material costs, and more importantly, a 30% reduction on average of the carbon footprint of concrete. So this is really a big opportunity. And again, this is something that we can do right now without the need for any new clinker or anything like that. And so as an illustration of the opportunity here is that if all the concrete producers in the world were using this solution and were using AI to optimize their concrete mix design, then we would prevent 500 million tons of CO2 from entering the atmosphere annually. So this is really a large number. This is more than the annual emission of a large country like France. So this is really a significant opportunity that can be achieved on the very short term. So here are a few references if you're interested in this work, and I'm happy to take any questions. Thank you.